Hi, thanks for listening. I'm going to show you some results related with a new wayfinder that we designed for its application in cosmological test. And we call this finder the popcorn wayfinder. So this plot here I'm showing you of Allen et al. I think illustrate one of the reasons of the precision cosmology era. The precision comes not only for the larger than ever data sets, but also for the joint analysis using different sources of information. I make a list here. What I'm going to focus in this talk is the exploitation of the galaxy distribution, and in particular, the use of cosmic void as cosmological probes. Before going further, we need to define what a void is, and the problem is there is no unique way to define them. Here we have some examples of void definitions. We can classify it into these three types. We focus in this talk in the third type that use this quantity delta, the integrated density delta, is the total amount of matter in a given region in comparison with the mean density of the universe. And this value is usually selected to be below a given threshold to get a void region. So at the end, the choice of your void definition depends on the specific analysis for which voids are intended. So there are mainly three types of cosmological tests proposed using voids. The first one is the cross-correlation of voids with galaxies. We have extensively worked on this test. Basically, using linear theory, it's possible to model this function and use it as a template to compare with measurements at different redshift. This allows us to perform a type of Paczyński test, similar to what is usually done with barrier acoustic oscillation test. Then we have the void intrinsic ellipticities. They refer to the dependence of the void shape distribution on cosmological parameters. It was shown by Park and Lee in 2007, but so far, at least as I know, there is no proposed test using this on real or void data. And finally, we have the voiced function that we are going to talk in here. This function gives you the number density of voids in a logarithmic interval of void sizes, and this function of the size of your voids, the comoving size of your voids. I don't have enough time to talk about to introduce the excursion-set theory to model this, but it's fair enough to say that based on this theory, mainly two models were developed, the Setten-Vandenberger model and the Jennings et al. Model. And using these models, you can measure this quantity in your survey and then use this like a template to fit different measurements at different redshift and perform a sort of Paczyński test using this function. The main problem for all these tests, and in particular for the voiced function, is the systematic errors. They arise mainly from three sources: redshift-space distortion, galaxy bias, and the void definition itself, for what we developed the popcorn wayfinder. Regarding the definition, we have a fragmentation problem, that is when a single region can be associated with several objects depending on your wayfinder definition. And then we have the integrated density estimation, that is that you need to obtain a complete sample of voids with a very well-defined integrated density contrast, and both the fragmentation and integrated density estimation are very important for excursion-set models. The popcorn wayfinder is a generalization of the spherical wayfinder that we have used before. So let's introduce it first. In a given trace example, suppose you have particles, galaxies, or halos, just like in this slice in this plot here in the right. You first estimate the density field and seal all the local underdense regions with seeds. You put their seeds. Then we make rho and a sphere located centered in each seed, and we look for the largest radius where the integrated density contrast inside this sphere is below a given threshold. after inflating all the seeds, we clean all the overlapping, all the spheres that are touching each other by favoring the larger ones. In this plot here, in the yellow curve, we have the abundance of spherical voids as a function of the radius. And as can be seen, there is a scale or size where they are most frequently found. But this is not expected for this is in physical field. This is not expected in a hierarchical scenario. What we actually was expected is to have a monotonically decreasing function. But all these voids here that we are not seeing are lost due to the shot noise. This is the joining between the shot noise spectrum with the distribution of clustering. So this scale is very important for us. This transition scale is separating the scale that are physical from physical. The popcorn void finder consists in a series of steps. We first run the spherical void finder and we measure the R-shot scale. Later, for each spherical void, we regularly cover its surface with seeds. Each seed is expanded one at a time, and we look for the largest radius of the second sphere, which a density contrast in the joint volume of this two-sphere system is below a given threshold. So in this way, we have the second sphere that expanded the most. Then, if this sphere has a radius that is larger than the shot noise radius, the sphere is accepted. Otherwise, the process ends there, and we have just a single sphere void. But if we have a second sphere, then we cover the joint surface with seeds, and we try to look for the third sphere that expanded the most. We expand one at a time, and we look for the third sphere that expanded the most, and then we have a system of three spheres that expanded the most. And the procedure is repeated iteratively until no sphere can be added with a radius larger than the shot noise radius. So here I'm going to show you a toy test using an elliptical Gaussian hole in a uniform random distribution. And as can be seen at the left, these purple circles are the spherical voids, and can be seen that they suffer of fragmentation problem. We have just a single region, this elliptical hole, and we have associated several different spherical voids. But when we run the popcorn void finder and we started with each of these spherical voids, we identified multiple times the same regions, but they are a lot of overlapped, and after we remove all the popcorns that touch each other, we just recover a single popcorn void. And the sequence of sphere correction that we add uniformly converges to the analytic expected in the analytic expected volume for this Gaussian hole. Okay, here I'm presenting to you the abundance of voids identified in a dark matter only simulation box. In the right-hand panel, we have a slice of this simulation, and as can be seen in the underdense region, we have nearly in every region we have spherical and popcorn voids. But the popcorn voids, sometimes they connect and merge some spherical voids. The important result here is the void function for popcorn voids in the cyan curve. The line represents the solid line represent the VDN model for different values of the excursion-set barrier. You can see when we increase the barrier, the abundance is shifting right and upper. But as can be seen, unfortunately, we cannot fit the spherical void distribution that is in yellow. The yellow cube is the spherical abundance, but the popcorn voids can be fitted for a given barrier. We can see when we compare spherical voids with popcorn voids, we see that they are less frequent for small sizes. This is the problem of fragmentation. There are much more abundance of spherical voids for the problem of fragmentation that we lost when we run the popcorn void finder, and we gain larger regions. The purple curve here is the popcorn void finder when you run it with a overestimated R-shot. I mean, when you select an R-shot that is too large in purpose. If your R shot is too large, if you select an R shot that is too large, you will see this wavy behavior, this undulation in your abundance that is not physical. And in the other side, if you select an R shot that is too small, then you get some funny results because you start to connect different regions, and the topology of your popcorns change dramatically. I'm going to show you here some results about the shapes of popcorn voids. Here we use a Monte Carlo approach where the joint volume is uniformly covered by using a set of random points that are properly weighted. And the shape tensor in this with this approach can be obtained by computing by summing over the whole point set. And when this shape tensor, you can compute the eigenvalue of the best fitting ellipsoid. And I am showing you here in the left panel a plot of the shape distribution of voids that can be seen behave very similar to dark matter halos. The dark matter halos are the solid line contours, and the popcorn shapes are the colors. The elongation of this distribution towards lower values of B over A and higher values of C over E, so C over B, sorry, indicate that they are triaxial ellipsoids with a preference to prolate shapes, similarly to dark matter halos. And in the right panel, we have the distribution of the surface to volume ratio as a function of the size of the number of members, and we have here the behavior expected for spheres and the behavior expected for triaxial ellipsoids. And what this plot telling us is that the popcorn voids have an intermediate behavior between spheres and triaxial ellipsoids. We'll now focus on the abundance of voids in the distribution of dark matter halos in a given mass cap. And the solid cyan line here is the abundance for popcorn voids in real space. As can you see, a good fit is obtained using the Zettelmann-Weiger model in this time, in the case of halos. If we assume that our observer is looking at this sample at redshift 0.51 from an adequate distance, and we are assuming a wrong fiducial cosmology, but without redshift-space distortion, we obtain shift in the comoving size of the Voisin function that we show here with the dashed and dotted lines. This is for a overestimated, and in this case, density parameter, and underestimated density parameter. And this geometry distortion, this shift, can be used just like an Paczyński test. With this formula, you can model this shift and fit the true cosmology. However, in the case of real samples, we need redshift-space distortion. So we have here the same analysis than in the previous slides, but now including the effects of redshift-space distortions. To do this, we added the peculiar velocity Doppler effect of the galaxy in the line of sight before applying the fiducial cosmology to compute the distance, the comoving distance. So in this way, we obtain a redshift-space distortion distribution in comoving space, and the voids, they tend to be larger due to the combined effect of redshift-space distortion and geometric distortion. However, we can correct for both AP and RZ distortion using the correction factor that we defined before in this work. These correction factors we have applied here. We have here the purple solid line is using the true cosmology in redshift space, and here again dashed and solid is over and underestimation of the density parameter, and then we get this shift here, and we have this additional shift in comparison with the real space distribution that is cyan just like before, due to the redshift space distortions. But when we apply both factors, they become more or less equal, and then we can fit using the Zettelmann-Weiger model and recover the effective bias that we see before. So as an example, I show you the 2D likelihood cuts of a cosmological test using this abundance in a lambda CTM box, where QRZ is now the target parameter instead of beta. Sigma 8 we have, and the matter density has target parameters, and we are assuming an effective bias has a nuisance parameter. And instead, we use a mock sample, a redshift 0.51, and this is effective for both geometric and redshift-space distortions, by assuming a wrong fiducial cosmology, in this case, lower values. The black stars indicates, in each panel, indicates the expected value has directly measured in real space box, or because the parameter obtained for the underlying cosmology. As can be seen, the test successfully recovered the expected values. All the black stars are for the most for the likelihood function, for the largest likelihood function, but we get a strong degeneration. So to perform this kind of test, you have to use, if you want to use an MC method, you have to assume a prior, because with the flat priors you get long degeneracy and the change never burns. But however, these have a great potential to be combined with others, because the bands are very narrow. So here are my conclusions. We have presented a new wayfinder. This definition is somewhat more friendly with Gaussian function cosmological tests, because it solves the problem of fragmentation and have a free form feature that allows you to adapt under dense regions. And also the integrated density of the object is very well constrained. And in this way, you recover a complete set of regions for scales larger than the shot noise. And these are very important features for the Gaussian function. The code is open source and is available under MIT license and in the repository in the slides. It's lack proper documentation, but we are working on that and we are willing to help. The Gaussian function in the matter field can be very well described using the VDM model, but in the case of bias tracers, surprisingly, we get better fits using the set and Van den Wagen model. We are not sure for that, but we think that is probably due to the constraint in the VDM model that is do not work very well for bias tracer samples. Okay, and then the formalism that we derive for fitting redshift space and geometric distortion describe very well and is very useful for this kind of test. So that's all. Thanks for listening.